Ugh, this shot is so hard. 145 meters. That's how far I need my ball to travel to get into that little hole. 5 iron? No, too short. 7 iron? I'm a little too experienced to handle that. Putter? Tempting, but a little ambitious. Driver? Yes, perfect. How did I come to that decision? In golf, as in life, choosing the right club is everything. You can't just grab the first one that feels right in your hands. You've got to analyze the angle, understand the trajectory, and make sure it gives you the maximum distance without overshooting.
In golf, every shot begins with a choice, which club to use. Each club has a different loft angle, meaning it launches the ball at a different height and distance. A driver has a low angle, around 10 degrees, for farther and more powerful shots that stay close to the ground, whereas a 7 iron or 9 iron has a steeper angle, sending the ball higher but not as far. Wedges create the highest arcs for short, precise shots onto the green. But the challenge doesn't stop once the ball lands. Golfers also have to predict how it will roll across uneven ground, like uphill, downhill, or along a curve in the green. Choosing the right golf club with the correct launch angle and using the right amount of swing force come down to predicting the golf ball's motion, a process that can actually be modeled and understood through calculus.
Okay, so now let's look at what happens when Alex hits the ball. So to describe its path, we use parametric equations. So we write both the horizontal and vertical positions as functions of time t. And the standard equations ignoring air resistance are x of t is equal to initial velocity cosine theta times t, and yt is equal to initial velocity sine theta times t minus 1/2 gravity t squared. So as you can see, the horizontal motion has a constant speed, while the vertical motion is affected by gravity, which is 9.8 meters per second squared. And this is important because changing the angle changes the trajectory of the ball. So shallow angles will give long ranges, while steep angles will give more height but shorter range. So the parametric equations let us predict where the ball will land by solving for the flight time and then plugging that into x of t.
Now we're going to look at a practice problem. Let's say Alex uses a 6 iron with initial speed of 48 meters per second and a launch angle of 24 degrees. Then find the time in the air and how far the ball travels. Assume that gravity is 9.8 meters per second. Okay, so first we're trying to figure out how long the ball stays in the air for. So let's set up our parametric equations. We have the horizontal and vertical components. So x of t is the horizontal distance after time t, and y of t is the height above launch level after time t. So we know the ball is in the air until it returns to the ground, which is when our vertical component y of t is equal to 0. So we're going to set this equal to 0, which is initial velocity times sine of theta times t minus 1/2 gravity t squared. And then since we're solving for t, you're going to factor out t, which gets you this, and then you subtract the 1/2 gravity t and divide by 1/2 gravity, and then you get this equation, which is the standard result for symmetric projectile motion. Then you're just going to plug in the numbers, and the answer is 3.98 seconds. So that is the time of flight. Okay, so now we want to figure out how far the ball travels horizontally, or in other words, the horizontal range of the shot. So to find this, we use the x component of our parametric equations, which is just x of t is equal to initial velocity times cosine theta times t. And we already found the time of flight from the vertical motion equation. So let's just plug in that value for t into our horizontal equation. So you get r is equal to 43.85 0 times 3.98, and then you get a range of 174.7 meters. 175 meters is the answer.
Alright, so now that we have covered what projectile motion looks like in a more algebraic sense, let's take a step further and see how this works with calculus, specifically partial derivatives, and seeing how different factors have an effect on the shot. If you're golfing and let's say you're 180 meters from the green, but there's also a 10-meter tall tree in front of you that's 50 meters ahead of you, the question isn't just if the ball will make it, there's more considerations such as how do I clear this tree and what matters in clearing this tree, swinging faster or adjusting my launch angle. So first, to go from the vector functions to creating these more complicated functions of multiple variables, you want to isolate t and then plug it back into these equations. So using the equation x of t equals initial velocity cosine theta t, you can divide out the initial velocity cosine theta part to get t to be equal to d equals initial velocity cosine theta, d being x of t. And then you plug that into t for both equations, and you'll come up with these two new equations, r being range or distance, which would be r theta v initial equals v initial squared sine 2 theta over g, and then y would be distance comma theta comma v initial equals d tangent theta minus g dt squared over 2 initial velocity squared cosine squared theta. So now you have these two equations that are multivariable, and the key idea now is that the height of the golf ball at any distance can be represented as a function that depends on these three variables: how far the ball has traveled horizontally, the initial speed of the shot, and the launch angle. So the height is telling us the ball's position vertically at any given point in its graph. And if you imagine plotting this in 3D, it would look like a smooth surface, but one where if you tweak the variables within it, you'll have a different result. So partial derivatives are how we measure these quote-unquote tweaks. When we take the partial derivative, as seen on the right here, of height in respect to speed, we're asking, if I swing a little bit faster, how much higher will the ball go, assuming I keep my angle the same? So we're holding certain variables constant while also changing another, which is, in this case, holding the angle constant. And then because when you're golfing, oftentimes if there's a tree in front of you, it's not just going to move. The distance will also be held constant when we're talking about a particular context of, I know tree is at X distance from me. So then, looking at this not just at measuring speed and the effect of speed on height, you can also take the partial derivative with respect to the angle. And then we're asking, if I change my launch angle by a small amount, how much higher will the ball go, assuming I keep my speed the same and the tree doesn't move? Each one isolates one variable at a time so that we can compare their effects directly, which you'll have to do for the homework. So once we find those derivatives, even just conceptually, we can evaluate them using the numbers in a shot. So let's say we know that the initial velocity is 45 meters per second and theta is 25 degrees. From there, we can see what those values mean. If the derivative with respect to the angle turns out to be larger, it means that the angle has a stronger influence on the ball's height. So fine-tuning your swing direction would make a bigger difference than hitting the ball harder. So that would be taking the idea of partial derivatives and applying it to golfing strategy. And then if the derivative with respect to speed is larger, then the opposite is true, and power matters more than the angle's precision. So this is basically, in a mathematical way, saying that adjustment is what we're focusing on when we're trying to clear an obstacle. And then the same goes for talking about range, where by taking its partial derivative in either theta or initial velocity, we could also have a similar analysis of how does launch angle affect how far the ball can go versus how does initial velocity affect how far the ball can go. And it shows that you have this control over where the ball lands. And when you take into account both of these factors, you can answer both the question of, does the ball clear an obstacle in its way, and does the ball reach the green? And so partial derivatives are very helpful in understanding why a golf ball is going to be successful in making it to the hole, but also understanding, okay, what parts of my swing do I need to tweak? And while physics is telling us the path of the ball, calculus tells us how much the choices in hitting matter, and that's the exciting part about partial derivatives in golf.
All right, so we're going to apply some more calculus concepts to golf. And here we're going to see how we can understand the slope of a green through gradient vectors. So let's start with gradient vector, and we'll sort of dive into it a little bit. What we know already is, right, z equals to f of x comma y. And so the gradient vector tells us the direction of steepest descent of a function. The magnitude of the gradient vector then represents the rate of that increase. Really, it's basically the vector pointing in the direction of the greatest slope of the surface. And it's represented by the partial derivative of each component of f of x, y. So it's going to be, it's like this upside down triangle. Gradient vector, or upside down delta, is then the partial derivative of f with respect to x, comma, partial derivative of f with respect to y. Cool. And we sort of explained it already, so we're just going to dive into a quick practice example, really easy. If f of x comma y equals x squared plus y squared, then gradient vector will equal 2x plus 2y. Cool. Now, if you had a point, you could put that like a 1 comma 2, you plug that in, you would find the direction vector that is the steepest descent of from that point. Another important thing to know is the directional derivative, which is equal to the gradient vector dotted with u, which is a unit vector in some direction. Now to quickly relate this back to our golf topic, what we have to see is on a green, for example, right? If you have a golfing green, and let's see, here's the flag. Cool. There's many hills and like sort of valleys on a green, right? And so what it can tell you is if you're at a certain point, say this is what the green looks like, the gradient vector will be able to tell you the steepest either downhill direction from where the ball is, or steepest uphill direction, right? So in this direction, for example, could be one gradient vector. Could be the gradient vector from that point, if it's some arbitrary x comma y point. And also, what the gradient vector can help you with is knowing how your ball will roll once it lands. Okay, so now we're going to dive into an example problem that dives back into the golf parts and really how we can use this gradient vector to explain things going on in golf. So here's an example. So f of x comma y equals 100 minus 0.03 x squared minus 0.01 y squared, and let's say golf ball lands at 5 comma 3, and find gradient vector of x comma y of at 5, comma 3, right? So if we were to compute this, right, the f of x of x comma y is equal to negative 0.06, and f of y of x and y is equal to negative 0.02. Y. Sorry, x and y. Okay, and then the gradient vector then is equal to negative 0.06x, comma, negative 0.02y. Now, if we plug in at 5, comma 3, then the gradient vector of 5, comma 3 equals negative 0.06 times 5, comma, negative 0.02 times 3. So at 5, comma 3, gradient vector equals negative 0.3, comma, negative 0.06. That's the gradient vector at 5, comma 3, and what it represents is the steepest, negative 0.3 and negative 0.06. The steepest ascent is in that direction at the point 5, comma 3. Cool. So that's our first answer. But the question can be expanded. So say, for example, there's some spin to the ball. Then there might be a different direction that it goes in rather than the ball may roll in a certain direction, right? What we take from the last problem is that the ball would most likely roll in the opposite direction of the gradient vector, right? So we would flip the sign. But if there's spin, let's say ball rolls in direction equals 3 over 5, comma 4 over 5. Well, in this case, we need to use our directional derivative formula that we have above. So directional derivative at 5, comma 3 will going to be equal to the gradient vector that we have dotted with the direction, the unit vector. And if we're working this, we get negative 0.3, comma, negative 0.06, dotted with 0.6, comma, 0.8. So du of f of 5, comma 3 is equal to, let's see, negative 0.3 times 0.6, plus negative 0.06 times 0.8. And what we would get is negative 0.228. So what does this directional derivative mean? What it means is basically if the ball rolls 1 meter in the direction of u, the elevation changes by negative 0.228 meters. So that point in the direction of u. When a golfer hits the ball, it travels through the air following a space curve, a path in three-dimensional space described by a vector function. So like if you've ever seen on TV when in a golf tournament, when the golfer hits the ball, they'll trace it in this red line. That's exactly what we're going to be doing. It's the space curve of the ball. And here's the general form of the vector function. R of t equals x of t, comma, y of t, comma, z of t. And we can say x is forward distance, y could be sideways, and z the height. Awesome. So now let's do an example quickly trying to match or just explain what the space curve would look like for a function. So if we have the function r of t equals 22t, comma, 4 sine 0.6t, comma, 28t minus 4.9t squared, how would we describe what this looks like? Or match it if we had to. So, x of t being 22t, the ball's moving forward at 22 meters per second. And since the y has a sign value in it, it means that there is some sideways motion, right? It sounds odd that how could it be moving from positive to negative, but realistically it doesn't have to. It's a very slight sideways motion until the ball hits the ground, right? And then in the z, we see this parabolic vertical motion under gravity, right? So if we want to compare it to other functions or see it on a graph, we can also find the maximum height by knowing it's when v of z equals 0. And v of z would be the derivative of z, so v of z, velocity of z, derivative of the position, so dz over dt, which then equals 28 minus 9.8t equals, if we set that equal to 0, we get t equals 2.86 seconds. Now, plugging that into z of 2.86 equals 28 times 2.86 minus 4.9 times 2.86 squared. And with that, we know that the ball has a maximum height, max h of 40. So that also can help us to determine what it would look like in a 3D path. That's just one way to do it. There's many others. If you see it and you can recognize it's going to be a parabola in the z, in the zx plane, and in the zy plane, you'll see this slight sideways motion as well as in the xy plane. And this we can see in the traces. As I move down, you see in the xy plane, there's a slight positive motion in the y direction, and the x is continuing. And then same in the zy plane. But in the zx plane, it's just a parabola with a downwards parabola. And that is how you get the path of a golf ball.
Oh, perfect.